Hello everybody, my name is Kenneth and in collaboration with my classmate Genaye, we're going to be talking about limits. We're both seniors in high school and we are currently enrolled in an AP Calculus course. As of December, the marking period is coming to an end and our teacher has allowed us to create this video as an assessment so that we can showcase our in-depth knowledge of limits. In this video, we'll focus on evaluating limits. More specifically, we'll focus on limits involving constants and limits involving infinity. We'll supplement this topic using examples from our trusty calculus textbook. We're not trying to confuse you, so if at any point you feel that the content is too dense, pause the video, take out a sheet of paper, and write down your questions. I'm sure your teacher will be more than happy to help you out, and just maybe you'll give us some feedback. So, sit back, enjoy, and most of all, welcome to the world of limits. In calculus, a limit is the value that a function approaches as the input approaches some value. What the definition is telling us is that for any number that we pick, we can go to our graph and sketch two horizontal lines as shown on the graph below by the red region. Then somewhere out there in the world is another number which we'll need to determine that will allow us to add in two vertical lines to our graph shown by the blue region. Now, if we take any x in the blue region, then this x will be closer to A than either of the points created by the vertical lines. If we now identify the point on the graph that our choice of x gives, then this point on the graph will lie in the intersection of the blue and red region. This means that this function value, f of x, will be closer to L than either of the points created by the horizontal lines. So, if we take any value of x in the blue region, then the graph for those values of x will lie in the red region. Now that there are actually an infinite number of possible x's that we could have chosen. In fact, if we go back and look at the graph below, it looks like we could have chosen a slightly larger x and still gotten the graph from that blue region to be completely contained in the red region. Also, notice that as the definition points out, we only need to make sure that the function is defined in some interval around x equals a. We don't really care if it's defined at x equals a. Remember that limits do not care what is happening at the point, they only care what is happening around the point in question. Okay, now that we've gotten the definition out of the way and made an attempt to understand it, let's see how it actually used in practice. They're a little tricky sometimes and it can take a lot of practice to get a good grasp of how to do this. So we're going to be looking at a couple of examples to work this out fairly easily. Here we have limits containing constants. We have the limit as x approaches c for x cubed plus 4x squared minus 3. Here we'll use substitution to find the limit, and we'll plug in c for x cubed and we'll plug in c for 4x squared. And then we'll have a result of the limit actually for the function of limit of x approaches c for x cubed plus 4x squared minus 3 as c cubed plus 4c squared minus 3. Here we have an example of where the limit does not exist. Notice that the denominator is 0 when x is replaced by 2, so we cannot use substitution to determine the limit. If we were to graph this, the graph would strongly suggest that as x approaches 2 from either side, the absolute value of the function values get very large. This in turn suggests that the limit does not exist. Here we have an example of limits to infinity. But first we're going to start with some background knowledge. The symbol for infinity does not represent a real number. We use infinity to describe the behavior of a function when the values in its domain or range outgrow all finite bounds. For example, when we say the limit of f as x approaches infinity, we mean the limit of f as x moves increasingly far to the right on the number line. When we say the limit of f as x approaches negative infinity, we mean the limit of f as x moves increasingly far to the left. The limit in each case may or may not exist. So, if we look at f of x equals 1 over x, and we try to find this as the limit approaches infinity, then we'll find that as x approaches infinity, 1 over x approaches 0. So we write out the function, the limit of x as it approaches infinity for 1 over x equals 0. Infinity is a very special idea. We know we can't reach it, but we can still try to work out the value of functions that have infinity in them. So let's start with an interesting example. So, what is the value of 1 over infinity? The answer is we don't know. The simplest reason is that infinity is not a number, it is an idea. So 1 over infinity is a bit like saying 1 over beauty or 1 over tall. Maybe we could say that 1 over infinity equals 0, but that is a problem too, because if we divide 1 into infinite pieces and they end up 0 each, what happened to the 1? In fact, 1 over infinity is known to be undefined. So let's say we want to evaluate 1 over infinity, or 1 divided by infinity. So instead of trying to work it out for infinity because we can't get a sensible answer, let's try larger and larger values of x. So for instance, let's plug in 1 for the value of x, and we'll ascend to 2, then 4, then 10, then 100, then 1,000, and then 10,000. If you were to let that happen, then you would get a graph about the one that you see now. So now we can see that as x gets larger, 1 over x tends to go towards 0. We are now facing an interesting situation. We can't say what happens when x gets to infinity, but we can see that 1 over x is going towards 0. We want to give the answer 0, but can't. So instead, mathematicians say exactly what is going on by using the special word limit. The limit of 1 over x as x approaches infinity is 0. My name is Kenneth, and on behalf of Genaye, I would like to thank you all for watching.